welcome to our last lecture on AI, introduction to AI. So it's just an introduction. Today we'll talk about robotics in general, some basic ideas, but let's start with our final group project. So the good news is I got my server up yesterday, so you have your API finally. Alright, so you can actually do testing. Right, so again, let's go to the task. So it is due the day of the show and tell, or you can call it exam if you want. So April 24th will be where you're going to show it to me, right? So idea is this: you'll be giving some address to explore, some space, two-dimensional space, and you have 200 exploratory steps, meaning you can do any values you want, and then you have a strategy where you exploit with 10 moves, but there's a limitation to this exploitation. You have to use only integer values, right? So meaning +1 plus -1, right? So you start somewhere and you exploit that area, right? So meaning you place your probe or your robot or whatever you want to call it, your bot, and it moves +1. It can move diagonally, right? But it has to explore that area, right? Exploit that area, right? So again, if you can think of better word than exploitation, I'm open to ideas, but that's what AI. That's an AI terminology. And so exploration, right? You have a huge space, but of course it's basically infinite. But so again, this is the actual API. Let's double check if it works now. Let's do it. This is a big test. On doesn't support. Yeah, continue the site. It's not secure. It's just a simple API, right? So you get something like this. It's a JSON. A JSON response, right? I'm sure you can know how to parse it, right? Pretty much any language will be able to. You don't even need anything fancier, so it will always be something like this. What happens if you go something bad? Let's say if you do something instead of 2.7, you put Valdis, right? Invalid value for y, all right? So if you put 5, it will start working again, right? If I put something here, right? If something RBS, all right? Invalid value for x, right? So pretty simple, right? I wonder if actually I forgot what happens if I do both. Yeah, you get x, the first fail, right? You don't get the both. But yeah, you see that's pretty simple, right? If you go here directly, you'll get the invalid value. So use xy, right? So those are your coordinates. You get back the z value. So simple, right? So any values or any valid numbers are valid exploration points, right? So in the real task, again on exam on 24th, you'll only have 200 tries to explore and 10 to actually get the values, right? So again, if you go here, it should work 0, 0. Of course, in this particular example, this first one, this 8080, which I'm giving you for testing, is relatively simple. Meaning there's something behind it, but you can actually determine it. In real life, and some other examples, it will be a little bit more difficult. Meaning there will not be just a simple function, right, behind it, right? Here you can actually do pretty well on this task, right? So I'm hoping before April 15th give you some more APIs, but they will be exactly the same thing. It's just the values will not be as simple, right? So again, you're not expected to go over -100 or +100, right? Mm-hmm. So that's a good news for you guys, right? Mm-hmm. All right. So how it will work on the April 24th, right? I'll open the APIs, right, and you will be able to run it basically, right? So last year I did on honor principle, meaning, but I did add the logging onto this. So I will see if somebody is doing like 10,000 calls, right, and hitting the API point, right, from the same API, from the same IP address, right? So it will probably be the same IP address, of course, but it's not active. You can check, of course, right, if you want, but it's not active yet, right? It's not active yet. So, all right. So, what do you submit? Again, so you can work in groups of up to 3 persons. Solo is fine, and you can do any language, Python, Java, Scala, Kotlin, Rust, any language basically, right? So you need, of course, all your names of you, right, in the first lines of main source code. And what do you submit? You submit your exploration steps, right? So of course you want to generate those, right, automatically. You don't want to do it by hand, right? I mean, theoretically you could, I guess, right? He'd be a human bot, right? Human calculator. You could do it by hand, right? Have a browser, right? And you don't have a code. You are like yourself, right? I don't know. I mean, I don't know how far you'll get there, right? So, and then of course you move, same thing, right? You enter these moves, right? So again, for exploration, you can do floats, meaning actually technically doubles, right? Or the integers, fine. On here, you can only do integers. And notice here, right, you are not allowed to exploit the same area twice, right? So you cannot do it, you find a good spot and you say you're gonna just extract oil from that place, or gold, whatever you want to call it, right? So you have to go around, right? So, and you cannot go back, basically. So this involves some care, right? So you'll have all integer. Notice how, again, you're allowed to move diagonally, right? So from 112 to 211, that's fine, right? But you cannot go back, right? So that's the idea, right? And this is now, I had a few people, students had problems with this, right? They thought they could just go, random spots. No, you cannot. You have to find one good spot and then explore that spot to the maximum, right? Okay. So grading. To pass, meaning, you'll get 6 or so. You'll have any sort of exploitation, and give some answer, right? Gives you something, right? It will work. It will be, it'll give a pass. So for one-person groups, I'll check the best out of 2. For 2-person group, best out of 3 API addresses, right? And for 3-person groups, best you have to do well on all 4 API addresses. Last year I added 5, 5th address actually. So let's see. Yeah. So, but I expect there'll be 4 addresses, right, to try, right? To not try, but actually work on, right? So what this means, of course, you need to have your program needs to be ready to take the IP address as a parameter, obviously, right? You don't want to, probably don't want to hard code it, right? You want some sort of command line argument, I mean, suppose you could have some other way of doing it too. Maybe some config file or something, I guess, would work, but probably just a command line argument would work best. Okay, so. I think I personally like this problem because it's relatively simple definition, right? And you can get some results. But to do well, you can explore pretty much anything. I had like 2 people who did actually some neural network last year, actually, in a class. It's not required to get a good grade, but you can. I mean, you can try some approaches, right? From it's possible, right? 200 because 200 answers, you have 200 moves. You're not going to be able to train too well, right? So it's interesting. It's the interesting approach. There are all kinds. You can try pretty much anything from this course or from for anything lots of different tries. Okay, now, so it's due in about 20 days, right? Roughly. So again, we do this on 24th. Right? So. Next week and the week after, I will be available probably through Teams. Maybe I'll come in someday. Maybe we'll do consultation if somebody really needs to, right? Probably on 10th, that means next week probably will be very short. But on Mondays I have more time. We can arrange it maybe. Also on Monday on 7th I will not be here. I have another appointment on Monday. So again, you feel free to write to me if you have any questions, of course, right? So okay. So let's do the last presentation on robotics. If there are no more questions on, you have a question?
No, it's just my head.
Okay, it's just your head. Okay, sure. Okay. Now, can you see actually anything there? Okay. Yeah. Okay, you can see it. Okay. Now let's go to our GitHub. Oh, come on, what's happening here? Come on, what is it? What kind of keyboard is this? English, right? No, it's like British or something. What is this? Yeah, it's some sort of weird keyboard layout. What kind of layout? Oh, United Key. Let's do English. Yeah, I mean United States. All right. Okay. Just in time. We just discussed the final assignment. Right. Yeah. But you'll see, now we'll actually have the lecture, but so the final assignment is live, and you can do it in groups, solo again. Yeah.
And how about the tournament?
Okay, so nobody asked me about tournament, right? So the idea is to do it tournament. We'll have one of the consultation days. What I'm thinking, again, since the next week is probably no go, because due to my other appointments on Monday or Thursday, it's all either 14th or 17th, probably, right? So I'll be here, and you'll be able to join if you have time. Hopefully you have some time to come. I'm thinking 14th. I'll shoot for 14th. Right, that'd be a good goal. So, you have anything else planned on 14th? Nothing. Okay, so 14th. All right. So again, that's my goalpost for me to go for 14th, right? So because it means I have to finish just doing the server basically, right? So lots of stuff. Right. No. Yeah, and like I said, you came in late, so the final assignment server is running right now, so you can do the, meaning this one here, right? This address here, like I mentioned already, this is live, right? Yeah, it's pretty simple, that's why I like it. But simple, but not too simple. Okay. Where are we? We're here. Wait. All right. Oh, this is our mic. I guess this is our. So I am recording this, but hopefully the sound is not going to be too bad on this. We have our duck. We have our code spaces. So robots. So what's your definition of a robot? Like compared to other agents, right? We do have this definition of bot, but robot in general, right? But you do know where it comes from, of course. The original term comes from where? From?
Czech.
Yes, Czech. It's a Czech. What was it? Something universal robots. RUR, I believe, right? The Czech writer from 1920s, right? We can check that, of course, right? A robot is a robot, right? It is not like this, but of course, right? Čapek, oh, Čapek, of course, right? So this was actually the Latvian version is not so good, but yeah, but so of course, robot, of course, is sort of, well, kind of like slave, and really, right? The version in Czech, Czech language, right? I don't know. We might come to regret that word, right? So yeah. So okay. Now I need to start again. All right. Right. So the main thing, of course, is that they're agents. They're physical agents. So meaning they have some physical part. It's not just software, right? And what they do manipulate. They do something with our world, basically, right? That's the basic idea, right? So again, they have sensors. They should have sensors, right? And they have what you call them effectors. Effectors meaning something that manipulate, do something, right? Grab, move, push, all kinds of. The whole world is effector. Effector. That's a big word, right? And now so. Let's see. So again, sensors, and of course, usually there is some sort of utility, right? There's some idea behind it, right? So goal for some particular robot is to maximize some utility, right? To yield the maximum reward, like to assemble the most cars in an hour, right? So I don't know, to stack crates, stack milk cartons, or of course, or move around the city, of course, right? So what makes, of course, this very complicated is they operate in a complex, partially observable, meaning they don't have the full picture of the world, right? And it's not deterministic, right? It's stochastic. Like all world, we don't really have the full picture. We don't know. Also, there's lots of seemingly random events. I mean, they may not be completely random, but to us and to robots, there will be some random element, right? It's lots of research started with these deterministic, these very easy environments, right? Where always you do something, exactly the same thing happens. But of course, in the real world, it doesn't happen like this, right? So also, what makes it hard is, of course, it's a continuous state, meaning it's not just like those robot dancing competitions, right? Like this, right? That's how early robots move, and that's how humans, the breakdancing, some of the robotic moves, right? But you want, of course, eventually have the movements have continuous state. Space meaning it's not just like this, but it of course moves, right? On some state. So floating point, so continuous, right? So again, challenges are of course because one thing is do a simulation. You can do some people have done really nice thesis actually here, especially on drones. Last year I had a student who did a really nice bachelor's thesis on drone. Again, drones are a form of robot, of course, right? So, it's just the thing is that once you move from the simulation to the real world, of course, you have something unexpected. The unexpected happens, basically, right? So this is kind of like where everything comes together, of course, right? You have your state estimation, planning, reinforcement learning. You have machine learning underneath, of course, right? All kinds of methodologies, right? So just a few examples of robots. So, right, so drone, of course, is a robot, right? So, but let's see, so what type of robots? So you have, again, the early robots, of course, like the ones you see in an assembly line, right? They don't look like don't look like Terminator, right? They don't look like they're not anthropomorphic, right? So meaning they don't look humanoid, right? So of course we see there is a tendency, right, to have these these humanoid robots, but I think it's apparent that they will not be the majority. There will be a lot of, again, already there's lots of useful work being done by robots which don't look like anything like humans, right? Because of course, I mean, if I have 2 arms, if you have 8 arms, right? So what was it? 2 legs good, 4 legs better, as in Orwell, right? Was it something like that, right? So you have 4 legs, you can have 6 legs, right? You have a problem falling down, you have a robot with 6 legs. But that's the issue, of course. Well, on one hand, right, it's kind of nice to have a humanoid robot, but there's that thing called uncanny valley, right? At some point they look kind of creepy, right? And then suddenly they are really realistic, and it's like, oh, everything's great. But if they're slightly off, that's scary, right? Right. So again, you see, so manipulators. So basically, they are robotic arms, right? So these are, of course, widely used, right? So also for not only for assembly, but also for individuals, right? You have, I don't know if anybody have friends or somebody who has some motor impairments, meaning some sort of disability. Well, you can't call it disability, I guess, right? But it is disability, right? So you can improve the life of that person. So of course you have mobile robots, right? Which of course now is a standard thing. Where they see a cleaning robot, where was it again? Some unexpected place. I mean, I know Lido has them, but where else do they see them? Some other place. IKEA probably had them, I think, somewhere else. The cleaning robots, you see them everywhere, right? They're like sort of like these kind of, yeah. So, no, the Lido has they had the dish collector one, right? You can put the dishes on it, right? Mm-hmm. Of course, kids have a lot of fun standing in front of it, right? So you can make it, abuse. It's a robot abuse, basically, right? So, but yeah, so legged robots. So for navigation of rough terrain, right? And of course, you have these robotic prostheses, exoskeletons, right? Winged robots, robotic swarms, right? So you can think again of an intelligent environment, meaning a room, a smart room. You can think of it as also as a robot, basically. It has effectors, it has sensors, right? So, right. So let's talk about sensors again. So we have the most popular probably is a camera, right? So passive sensors, cameras, and you have active sensors. We talked about this last time about computer vision, right? Big part of robotics is the computer vision. It all comes together in robotics. You have sonar or radar, a different type of active sensing, right? Like what bat does, right? Bat sends sonic waves, and you get back some reflection, right? So it seems like, again, you do need some active sensors to achieve some it will provide better performance given everything else is given equal, right? So you have rangefinders, right? So I mentioned rather tactile sensors, right? So things for sensors for touching things, of course, getting some feedback, right? Again, location sensors. Okay, of course, you think, okay, yeah, we know GPS. Actually, GPS is extremely difficult field, but it seems to be solved, but it doesn't solve the localization problem completely. Why? So, because first of all, indoors, GPS does not work that well, right? Also, GPS is not that precise, right? GPS is not that precise, right? There are also some, originally it was due to military restrictions actually, right? But also, yeah, if you need a clear, like up to centimeter or a couple centimeters localization, few centimeters, you can't use GPS for that, basically. You need something else, right? So proprioceptive sensors, right? So basically, it's what's happening with your robot's movement, right? What kind of, how many degrees it moved, right? So again, you need those as well, right? Again, you notice the cars have these things too, right? So also the force and torque sensors, right? So you have delicate manipulation. You're trying to rotate something. You need to have this torque, force of being applied, sensor of what's happening, what kind of resistance you're getting back, right? So all right, yeah. Yes, this is, of course, these pictures are old because meaning from last year, right? The new AI models would work even better, but seems to they see okay, right? So there's some arms missing or something, right? What is that there, right? Looks like an arm or something, or some tools, right? Robot changing light bulb, right? Difficult task. So how do we, so now we have our sensors. We need the actuators. We have the effectors, right, in general, in total. So some of those are what? We want to move, right? So actuators, right? Electric, hydraulic, pneumatic. What's pneumatic? This one here, what this word means? Well, it says here, pneumatic actuators use some sort of air, right? Pneumatics, I can't, I think it's called pneumatic, I believe, right? So some compressed air, right? Hydraulic means use fluids, again. So your basics, so that's why you're taking physics, right? I know you guys, you had physics last year, right? Yeah. I know you hated it, right? A little bit. It's okay, right? But in general, that's why it sort of makes sense, right? Again, if you do, knowing a little bit of, tiny bit of physics, right? Just a tiny bit, right? So, yeah. Okay. So rotation, right? There are all kinds of, doesn't have to be humanoid, right? Of course, 3-hand grippers, right? Like the one in all those claw machines, right? In the, like in the Toy Story, right? And of course, all arcades, right? But they're simpler, right? But of course, for a human hand, right? You need, like, to emulate a human hand, you need at least 20 actuators. I guess it's, let's see, how do we call 20? I guess 1, 2, 3, 4. 4 times 5, I guess, roughly. I guess there's 4 movements possible, right? So extremely complex, right? So this one here, that's a shadow dexterous hand, right? Pretty cool, right? So what do we solve? So what issues do we have in robotics, right? So there's various models how we can approach robotic problems. So, right, we can have this Markov decision process, right? When we know there's some randomness, but it's fully observable, right? Again, usually, of course, we'll have. Excuse me?
Oh, sorry.
No. Okay, so we have also possibility of partially observable Markov decision process. What this mean? This means that we have some. We don't have the full picture basically, right? But also it's stochastic, meaning there's some randomness as well. So of course you have a game, right? You have multiple agents, right? Robots playing soccer, right? Or robots playing soccer. This used to be a fun field, right? A video, some, lots of fails. Now I think they're getting much better, right? Right. So they're getting much better now, right? The early ones were really funny. Now, not so funny anymore. It's serious business, basically, right? Yeah. So again, you can see how much. Again, it's a wide, extremely fast, quickly expanding field. So robotics basis, you are multi-agent, meaning there are multiple agents, human agents, right? And of course, you need to handle both what? Cooperative and competitive dynamics, right? First of all, you want to cooperate, right? If you see in this, it's kind of hilarious. I saw this in Los Angeles, I believe it was last on Christmas. So you have these delivery robots. I'm sure it's also in Estonia. You've seen this too, right? They're all trying to cross the street. How polite they are, right? But of course, there's a backup of other ones coming after them, right? So there's a little what you call traffic jam. I guess you call it traffic jam for robots, right? Because they're playing it very safe on trying to cross the street, right? They're afraid of cars for a good reason, right? So, and we know how people abuse these robots as well, right? So, again, so this means is, and now we come to, of course, one of the big challenge. This could be like the missing lecture of ethics, right? The reward functions, right? How do we they have to act in the service of humans, right? So we have to align with human needs and desires. But problem, of course, with this is that what if it's serving like, I don't know, one person's needs, and maybe it's hurting 100 other persons. So this cuts really deep into ethical questions. And I'm not even going into the military use of robots, which is unfortunately, coming, right? So it's happening actually, right? So very, very, very deep issues there, right? So also, one of the tricks we use in robotics, of course, is decoupling perception from action. Meaning, we have this informational gathering step, right? But also to do something, we have separate tasks, right? Of course, when we do it, humans do it, we kind of sort of like we have lots of things happening simultaneously, right? So again, so we have task planning, motion planning, control, preference learning, people restriction, right? Then you have to put all this together, right? You have to put all this together, integrate this, right? You might have something really cool vision algorithm, right? You can detect cars or whatever, or happiness or something, but how do you integrate into actually a working system, right? So perception, right? So again, this is learning something, right? So you want to translate these sensor measurements into something, into your internal model. You need to actual some data, right? So what do you need? So you need to probably, it's like human eyes. You probably see this, that you might have read about this, how humans perceive actually, right? We have the illusion actually of seeing something in a room. Instead of doing something, saccades, I think it's called saccades, I think it correctly, yeah. So this is what's happening, rapid eye movements, right? So this National Institute of Health, I hope it's still around, right? So they're not defounded yet, right? So, right, rapid eye movements, right? So basically, what we see a continuous picture as humans, right? But it's not the true, right? Instead, we are doing, our measurements are actually happening continuously, right? Our perceptions happening continuously, and we are building this, so to say, image of our world continuously, right? So we're sort of faking it, because first of all, another thing is, of course, another trick is we have a blind spot in our eyes, between our two eyes, basically, right? There's a trick you can use. You close one eye, or with one eye, you can see where there's this tiny, blind spot. This blind spot is what? It's your retina. It's a retina, I believe, right? So, right, which you don't see anything there, right? But if you have two eyes, right, you're good because it compensates. If you have one eye, you actually have to fake it sort of completely, right? And there are tricks you can do this. I'll show you this in a moment. Again, some more visual. This also goes with the visualization, with the computer vision. All right. So perception. Okay. Yeah. So see also the human. Compare with human. Compare with humans. Let me put it here, right? Compare with human perception. Comparison with human perception, right? Okay, it's right. Types of eye movements. Yeah. Okay. On et al. Right. Also, yeah, the blind spot, blinds human eye blind spot, right? Spot test, right? It's basically, yeah, right. You can have this, but you have to print out, right? So you can find your blind spot here, basically, right? Association for Research in Vision of Ophthalmology. Right? Again, if you go to your vision specialist, your eye doctor, or even your eyeglasses doctor, they will be able to tell you where your blind spot is, right? So this can be something you can test for blind spot. Right, blind spot tester, right, something like this, right? All right. So something to look at. All right. So. Human perception also is not continuous. Continuous. Come on. I'm lazy. Yeah. Right. So. Right. So. Saccades. Right. Visual processing. Right. All right. All right. All right. So now we come to the other hard part, of course, which is localization mapping. So idea is that we need what is localization. It's a subfield of robotics again. So determine where the robot is, right? So let's say if you think of a wall as two-dimensional wall, ignoring z value, right? You can think of a robot as xy, right? Yeah, where it is, but also heading, so that's the angle, right? Where is it pointing at, right? That also might be important, right? Where it's, because robot pointing to the backside or the other side, is assuming it's not omnidirectional, all directions robot, right? So how do you localize? So there's two big subfields, central models. One is landmark based, means there are specific places, right? Which say okay, I am, middle of center of city, center of room, or I'm a corner of room, specific corner. It's only giving you these coordinates, right? So landmarks, right? This approach has been used also in not geometry, but not metrology. In human, when you're doing measurements, right? I forget the word now, right? So landmark based, and of course the other one is range scan, meaning you try to do localization, not have it. You don't depend on the landmarks, but you actually measure what you see. But of course, the best systems utilize both, right? In fact, again, if you see in your phones, right, sometimes or also your computers, right, they ask to include the localization settings, right? How do they determine your location, right? Well, they have, of course, IP address, which is easy, right? But to get down to actually your location, of course, your phone uses GPS, but GPS again is not precise. So the trick Google and Apple and other companies use, of course, is that you have Wi-Fi connections. They have coordinates for the Wi-Fi connections, and again, you can from multiple measurements, right? If you have 5 people, assuming you have GPS, right? Again, they connect to the same network. You can, as more and more people connect to the same Wi-Fi spot, you can actually determine where the Wi-Fi spot should be, actually, the precise location, right? So, because again, it uses also Kalman filter, right, to do this. So assuming some noise, again, you assume the noise, right? So Kalman filter works really well. So simultaneous, again, I mentioned this before, simultaneous localization mapping. So if you don't have any map, right, so you need to do both. You need to map the situation and also localize within it, right? So look at here. So this is, if you have noise, right? Let's look at this case, right? So Monte Carlo localization, right? So initially, maybe I'll make this bigger picture. Let me see here. I'll put the picture so you can see this a little bit better. No, that's not that picture. Control C. Okay, yeah. All right, maybe a little bit bigger. Yeah. Okay. So, all right. So initially, the robot space could be anywhere, right? Then after a while, right, you come across the second one by model. So this indicates that there's high probability of robot being either here or here. And slight probability of somewhere else, basically, right? Eventually, of course, this is unimodal uncertainty, meaning, right? So you enter a room, you know for sure you are here, right? It's pretty much a given, basically, right? There's no, there's almost no other choices, basically, right? Of course, compare this to the initial one, right, to these two possibilities, right? So it's either here or here. So this means, okay, let's look at this example here, right? So again, so this, because why? It looks like these doors kind of look similar, right? So it's either here or here, right? Assuming there's mapping done of this map, right? The robot, without any other, if it doesn't have any special landmarks or anything, like is there a special landmark here? Of course, you know, oh, I'm here, right? So that's what you say. You have a tiebreaker. You have some landmark here, or you have extra extra sensors, right? You say, okay, my localization algorithm, okay, says, okay, I should be here or possibly here, right? Then you need some sort of tiebreaker or something to give you the last final push. If there's like some sort of beacon here, right? You say, okay, this is closer to that beacon, so I'm almost certainly here, right? I mean, I could be maybe here, but most likely I'm here, not here, right? So this is of course ideal, but this doesn't happen that often, right? So, all right. So, where's my? Okay, let's continue. Right. So there's a way of how you can do this, right? Monte Carlo localization. I have some code. I don't know if is this visible? I forgot if it's visible or not. Yeah, no, I don't think it's visible. So it's not interesting to run, right? So, yeah. So another type of perception, right? Yeah. So how about other perception, right? Smell, right? Well, I think they're pretty bad right now. I have not really done much research on smell sensors, right? It's actually one of those things which is really underutilized, right? First of all, producing good smells is not really, synthetically, is not very well done yet, right? Maybe for a good reason, right? I don't know, right? But also the sensing of smells, right? It's not really, there have been some Nobel Prizes actually in medicine for some, even in the last 30 years, for some critical discoveries in smell, on human smell perception, but it's not fully, so we still don't know exactly how we smell, basically, right? Our noses work, right? So obviously you have other sensors. We didn't talk about, I mean, we don't have to have human sensors. Like you have, for example, there's nothing preventing a robot from having infrared or ultrasonic, right, sensors, right? You have all kinds of sensors which are not beyond human abilities, of course, right? So now let's go to talk about supervised and unsupervised learning, robot perception, right? So machine learning, right? Again, it's quite critical if you want your robots to improve, right? So especially if you don't have your optimal, you don't have an optimal set of rules what you can do, right? So machine learning can help you map this whole, you have this whole sensor space, all these, we call them features, right? You have some measurement, you have a bunch of features, bunch of measurements, right? And you want to maybe model into something usable, maybe lower dimensions, meaning only two-dimensional space, maybe, right? You have like 50 measurements, right? But all you really care is X and Y coordinates, for example, right? So you don't really need all of these, but you can use machine learning algorithms to do this, right? So now there are ways of against unsupervised learning, right? There's low dimensional embedding, meaning basically you transfer this data into lower dimensions, right? Self-supervised learning, right? So robots collect and they label. That's the best of the world, right? You can have a robot collecting and taking samples and actually providing answers, right? That's very useful, right? So idea, of course, is that you need, of course, some starting points as well, right? So from a human or from other robot, of course, right? So again, if you have a dynamic environment like autonomous driving, right? Of course, where everything is unpredictable, right? You need some way of continuously updating your priors, updating your belief state, right? Because it's going to change, right? It's not going to be fixed. Okay. So planning, of course, you'll need your classical path finding algorithms. Include those if it's important, right? So motion planning, right? A lot of space is involved in there, right? Configuration space, right? If you have three-dimensional space, and the motion planning, again, we talked about this a little bit, right? So visibility graphs, right? Again, how you do this, right? Yeah, Voronoi diagrams is one way of planning the movement. So the composition, right? Yeah. Randomized the configuration planning, right? Exploring trees, kinetic planning. I'm saying something interesting here for now. Plans versus policies, right? So, plans versus policies, right? So, So there's these two terms. So what's a plan and what's different from policy, right? So plan is a set of specific things he has to do, right? So a robot, or any agent, in this case robot, cannot deviate. It's a plan, right? You have to do it. Do this. A policy is sort of like in real life. Policy says, okay, what's our best practices, right? What's your policy, right? I don't know, on tipping or dressing, right? Dress policy and so on, right? Plan is you have to dress special way. For example, plan says, okay, you have to dress only in all black, right? Policy says, okay, it's best to dress in dark colors or something like that. It's a simple example, right? But so again, the static plans, right? The static plans, you want to move to these general policies, right? So again, because plans change, right? Plans change, right? Policies are so more robust, right? So they're guidelines, right? They adapt. Policies adapt. Right, we can adapt like in the politics as well. We adapt, right? So now optimal control, right? There's optimal problems, all kinds of things, uncertain movements, right? So how do you adapt it uncertainly? Reinforcement learning, right? So reinforcement learning is what we have. What's needed? Reinforcement learning, some sort of reward, right? Some sort of reward function which gives you something, right? So you need to reward the robot, right, for doing well, right? So your agents do, right? So, so for example, one thing is when you're learning, like in this example, like your final project, right? You think, okay, it's for a robot, right? Well, if you go to some, you go to some API call, right, and you get a really bad answer, right? Like if I go here and I get like I go to 5 something, right? I get -1,000. I'm on the bounds, and let's say -1,000 represents death, right? Well, if you have an emulation, no big deal, right? However, if it's an expensive robot, right, you don't want it to fall off the cliff, right? You don't want it to fall off the cliff. This represents a cliff or lava, right? So you have to be extremely. Your priority is your loss, but you want to avoid catastrophic loss. Like that moon probe, which failed, what is it, about a month ago, right? Private moon satellite failed. Not satellite, it's a probe actually failed because it was something. There was actually the programming problem with the code bug, and basically they landed in a place which was really dirty actually, right? And all the sensors clogged up. And then it fell over, and then it fell off on its own. And basically, I think the issue is that they had the solar batteries were all dusty, basically, and so they couldn't draw enough power, right? You hear about this, like the private new moon landing, right? Yeah, false silent, right? This was Firefly, right? Yeah. So this is it was not a Firefly. No, this was a good one, but the other one. There's two actually. That's the funny thing. There's two privately financed probes landed, right? Yeah. The first one went well, right? The other one was. It's not hilarious if you are working with a company. Actually, I read somebody who's worked on that project. It was really painful. He might have even worked on the code, right? And that really sucks, right? Athena was the one, right? Intuitive machines, right? They had like billions in financing, right? And they failed. And this was the second try, right? That was the worst. They said after the first fail, they said, okay, next time we'll get it right? So they say, okay, basically it's too cold, right? And of course they knew this is too cold, right? It's just that basically they did not have these. They had these safety considerations, and they still failed, right? So again, right? So if you have a chance. When you don't want to really, when a complete failure is really a game ender, right? Then of course you act differently, right? If you're walking a tightrope, you will be acting differently, hopefully, than if you're walking along a regular street, right? So again, change or same goes for robots, right? So you need of course some sort of good reward function, right? Now ensuring safe exploration, right? Good models. And again, so this goes back finish, right, of course, the context of human-robot interaction, right? So, again, space exploration, like, of course, is natural for robots. There's some people who say we should only be using robots for Mars, but I think humans also have a place, right? We also want to go to space, right? So, how many of you would go to Mars mission? No. No one? No. Too dangerous, right? But you want to come back, right? Right? Yeah.
Preferably.
Yeah, preferably, right? So yeah, okay, but yeah. So again, an extra challenge is of course optimizing robotics and collaboration. Meaning, if you have a robot assistant, right? Of course, a robot should not only be efficient by itself, right? But it should also, of course, synchronize what the human wants, right? So win-win. But of course, again, because for robot, of course, we assume we don't give it agency, right? Meaning there might be agents, but they don't give them full agency, right? Of course, so the human utility is over the robot one, right? So basically, the robots must have the reward functions that reflect the actions outcomes of humans, right? So of course, you might have heard, right? Because especially considering that humans are not really rational, right? None of us are fully rational beings, right? We have all our irrational things, and the worst thing is, of course, our actions during day, right? Our rationality changes, right? Like in the morning, especially if you're hungry, right? Your rationality goes out the window. You'll do stupid things. You're hungry. It's been proven, right? Of course, that people, when they are hungry, they're angrier, they're more irritable, right? And so on, right? I hope you're not too hungry at the moment, hopefully, right? So, all right. So we are approximately rational agents, all right? So, right, all these problems, like I said. So predicting human action is really hard for a robot, right? Because humans are not rational as much as you want to see. So they're kind of like a black box, really. So your robot has to do this learning. What God is Asimov? Is there Asimov? No, Asimov, no. Right, of course, Asimov, who was a science fiction writer, Asimov's 3 laws of robotics, right? This was done in like 1950s, right? 3 laws of robotics, right? A robot might not injure a human being. Through an action, allow a human being to come to harm, right? Handbook of Robotics, 2058. That's near, that's only 30 years, right? Right? That's pretty soon, right? That's 56th edition. So the first edition shall come out like recently, right? But of course, right, this is written like about 1950s, of course, right? A robot must obey the orders given it by human beings, except where such orders would conflict with the first law, right? So, and then of course the robot must protect its own existence as long as such protection does not conflict with the first or second law. And of course, he basically wrote a lot of stories about these edge cases when you have these 3 laws, right? And sometimes seems like the robot is not obeying these laws, but turns out it is obeying, right? So almost all, so it's a safety feature, right? So the thing is, many of these stories, of course, it turns out that robot is doing it, right? It's not, the laws are being preserved, actually being obeyed, but due to some other human or non-human element, of course, it is, there's something unusual about the way the robot applies these laws, right? So, the 3 laws of robotics, let me add that, right? It will be sort of, right, we will add this, right, the 3 laws of robotics, right, application domain. So, yeah, so we have our application domains, home care, big field, right? Personal robots, yes, supposedly there's some cleaning robots right now, supposedly, right? Last year they introduced them, right? Healthcare in general, services, right? Autonomous vehicles, entertainment, right? Exploration of hazardous environments, right? Industry, right? So, and again, right, book. On, let me add some, let's empty cell, right? These are Asimov. Yeah, all right. What's it? A robot, there's a 4th law. There is a 0 law. A robot may not harm humanity, or by inaction allow humanity to come to harm. So this is the thing. true in action. If robot is like, if there is a human being hurt, the robot is obliged to help, right? You can't just say, right, if somebody is drowning, a robot is supposed to jump in and help, right? So ethical implication, this has big implications. So, right, limitation of critiques, right? Yeah, they seem like there's a huge cultural impact, right? Yeah, right. So, well, yeah. All right. So, I recommend that you check out some of his books. You know, pretty good writer actually, right? There's also robotics blogs, right? Probabilistic robotics, right? Yeah, Sebastian Thrun actually, well, quite controversial person actually, right? I think he left Google with like a couple $100 million and tried to do his own startup or something like that. I forget who hired him. It turns out he took all the Google code with him or something like that. It was, if I remember correctly. Right. So there's lots of historical notes, right? So there was a myth of robots, right? Even Aristotle thought about robots, right? So Shake is a robot, right? Right. DARPA challenge. There used to be autonomous driving challenges, right? Now, of course, right? Now these days we have Waymo and things like that working already, right? Robots to beat human soccer teams. But I don't. Okay, so that's interesting. Like, so there's this initiative to beat soccer teams. But if you think about it, of course, it depends. You have the rules. Like, what kind of robot can play soccer? If you put a robot which moves around, you put the soccer inside and it goes through, and and it destroys the humans on the pass, right? I mean, it would win, right? But of course, I guess the rules are to actually have to obey certain humanoid rules, how it moves, of course, right? So, yeah. Interesting. So, okay, so that's it for today, and actually for the course. I hope you had an interesting course. It gave you some interesting starts, some ideas to think about AI in general, because the field is expanding quite a bit. So we saw all the subfields, right? You just touched base on those, right? And hopefully we'll have some more. You guys will have more exploration, right? Okay, so. I'm done. How about you guys? So learn the 3 laws of robotics, Isaac Asimov's, right? Read some of the books when you have a time. All right, and I'll see you guys. I'll see you on 24th, right? And possibly I'll see you also. Hopefully, I would see you on 14th, right? For the Go tournament, Gomoku tournament, right? You don't have to, but hopefully you'll be able to come as well, right?
Maybe you could make a Zoom for that?
Yeah, maybe I'll do Zoom as well, right?
Yeah.
All right, guys. Thank you, everyone.